Hi Level 3s and welcome to Level 3 3.4 Atomic Structure and Bonding, and this is your third lesson. Here are our learning objectives: to describe the key features of the periodic table just really quickly, and to then describe the periodic trend of atomic radius and ionic radius. This will probably take 2 videos, so it'll be in 2 parts. So here's a do now. Please feel free to pause, and here are the answers. Any questions, jump on Teams. Okay, so some key features that you should know of the periodic table. This is the one that you're going to get in your exam. This is the NCA Level 3 one that I've shown you before. Should know by now that these numbers up the top are called the group number, and the group number tells us how many valence electrons an atom has. So if something's in group 2, it's got 2 valence electrons. If something's in group 15, you forget about the 1 and it's got 5 valence electrons. So those are group numbers. Here we've got, they don't write them on your periodic table, but here are the period numbers, and your period numbers tell you how many energy levels are occupied by that element. Okay, so you've got a staircase going on over here, and I'll show you it more exactly on the next slide, where you have metals on the left and non-metals on the right. I know you guys know this stuff. This is a very quick recap. The atomic number here, the smaller number, that tells you the number of protons in the atom. Really important for where we're going with this topic. That also happens to equal the number of electrons in the atom, okay, and the mass number here, that stands for the number of protons plus neutrons. Now we know that these groups have names. These are the noble gases, okay, and these are the halogens. Those are probably the most important. This here are your transition metals. Okay, and then you've got your alkali metals here and your alkali earth metals, less significant to be honest. Okay, that's pretty much it that you absolutely have to know going forward from here. So let's get started. Okay, oh, here's just another picture of the periodic table. You can see the non-metals in a bit more detail here. Okay, so the periodic table, what does it tell us? Lots and lots and lots. Elements are placed according to their atomic number and reactivity. That's probably the biggest one for where we're headed on this. Remember, elements in the same row, that's called a period, and same column is called a group. So no longer can we use column and row. Hopefully you haven't been for a few years now. So what is this part of the topic? This part of the topic is periodic trends. We're going to be covering 3: atomic radius, ionization energy, and electronegativity. So today's lesson is all about atomic radius and ionic radius. And as you can see here, this arrow says atomic radius decreases this way and atomic radius increases this way. So that's what we're first going to discuss. So what affects the reactivity of an atom? Well, there are multiple things. First of all, we've got to remember that the part of an atom that takes part in reactions is the valence electron. So we're always concerned about the valence electrons, and what's actually holding them in place is the nucleus here, the positive protons in the nucleus. Remembering all attractions in chemistry are electrostatic in some way, meaning the attraction between positive and negative. So we've got the positive protons here and the negative outer electrons. Okay, so that's what's causing everything here. One thing to note is that it's not 1 proton for every 1 electron. So let's say that there's 15 protons in this nucleus. Okay, that means that all of those 15 protons are exerting a positive charge on all of the electrons at once. So it's not 1 for 1, which is a really common misconception. And I'll keep repeating that as we go through this topic. So what is going to affect the pull on those valence electrons? And there are multiple things. I've got 3 listed out here. The first one, and so these 2 here, sorry, I'll just start by saying these 2 here need to be in all of your answers. Okay, so every answer needs to have these 2 things, and these won't make a lot of sense until we go through a couple of answers. So the first is nuclear charge. So nuclear charge is caused by the number of positive protons in the nucleus. The greater the number of positive protons in the nucleus, the greater the nuclear charge. Okay. The second thing is the number of energy levels. Okay, so you could be talking about across a period, which means you're talking about the same energy level, which you would state, or if you're talking about down a group, then you're talking about between different numbers of energy levels. The two factors you need to talk about are shielding from inner shell electrons, and that's like a parrot phrase that you're going to repeat for NZQA. If you simply write shielding, you'll not get into the excellence category. So it must be shielding from inner shell electrons, and in a moment I'll explain what that is. And the second part here is quite easy to understand, and that's distance from the nucleus. If you've got a greater distance from the nucleus, well, then the valence electrons are going to be held onto less tightly. And that's quite logical. So what is this shielding from inner shell electrons? I'm just going to show you a couple of slides down. So this one here is a good example just to quickly show you. If you look here, this is a valence electron. So if this nucleus is attracting this valence electron, or all the valence electrons it would be, the one part that's going to impact that attraction is how many inner shell electrons there are. Now, shielding is actually a bit of a misleading term because it kind of makes it sound like the electrons are being blocked, like they've got some sort of barrier in front of them. That's not actually the case. When we say shielding by inner shell electrons, what we're really saying is the more electrons that there are between your valence electrons and your nucleus, they all repel each other. So electrons, as we know, have a negative charge. So this negative charge is repelling this negative charge, which is repelling this negative charge, and so forth. So all of them are repelling at once. And because there are lots repelling each other here, that actually weakens the attraction. Okay, so the more things there are repelling each other, of course, is going to weaken the attraction between that positive, this positive and this negative. So when we say shielding by inner shell electrons, the other way that you could say that is electron-electron repulsion between the inner shells, because that's really what's happening. Okay, so when we say shielding by inner shell electrons, we just mean there are more electrons in these inner levels repelling each other and weakening the attraction. So I'm going to move back now. Okay, so that's shielding from inner shell electrons. Remembering you could say more electron-electron repulsion in the inner shell levels. That's fine. But you have to be quite explicit to say inner shell electrons so we know what you're talking about. The third point here, electron-electron repulsion in the same energy level, this mainly comes up with ions. So I'm going to take a pause on this third point, and when we come to ions, which will be in part B of this lesson, I'll discuss that further with you. Okay, just a wee bit of a recap to make sure you understand it's valence electrons that take part in bonding. Okay, I'm not going to go through this, we all know this, but it's just highlighting it's the valence electrons that are doing the part. Okay, so as I said before, the two things that you must talk about every single question are nuclear charge, so that's the number of protons in the nucleus, okay, and the number of energy levels, and you must explicitly state when you talk about the number of energy levels, the shielding by inner shell electrons and the distance from the valence electrons to the nucleus. If it's an ion, we'll talk about this, but that's a bit later on. Okay, so just a reminder again, I did say this earlier, a big misconception is that it's one proton per one electron, okay, and this is not the case. Because all the protons are concentrated in the nucleus, that nucleus has a centralized positive charge, and it exerts that positive charge on all of the electrons at once. So it's not that each electron gets 1/15 of the nuclear charge, okay, or in this case that should actually be 1/11 because there's 11 protons in the picture. Okay, now effective nuclear charge, you'll often see this in textbooks. IB actually talks about this a lot, but we don't talk about it in NCEA. So you don't really need to worry about it at all, but if you see it, you can just ignore it. We're not going to include it in NCEA answers, so I'm actually not even going to explain it. I'm just going to move on. So here's the general trend of atomic radius. Okay. The size gets bigger as you go down a group, and the size gets smaller as you go across the period. Okay, and we're going to talk about why that is now and exactly what is atomic radius. So atomic radius is calculated between the average distance between the nuclei of two atoms. So here's the nuclei of one atom and here's the nuclei of another atom. Okay, now you'll see these two pictures here, and there's actually good reason for this. So most of our periodic table utilizes this type of bonding, and that's because most atoms, when we do this, we measure the atomic radius of the atom bonded to itself. So if we're looking at the periodic table, any of the metals on the left-hand side can be bonded to themselves. That's how metals exist in a metallic lattice. So we just have the distance between the two nuclei of those two metals, and we half it, okay? So that's, or if we're talking about a non-metal, non-metals form covalent bonds. Again, metallic and covalent bonds are very strong, and so they just measure between the two nuclei, and it's pretty similar. The part that gets a bit off in this example is this one here, and this actually is talking about your noble gases. So our noble gases, like helium and neon, they don't form bonds with things because they're stable, and so therefore the only type of attraction that's really between these is actually weak intermolecular forces, okay, which aren't very strong, as we know, and therefore the nuclei are not being pulled in as closely as they will be for your metallic and covalent. So that's why when we look at a picture, like I think I've got on the next slide here, I'll come back to that. So here, your noble gases sometimes will look inflated in certain diagrams when we look at atomic radius. So that's why they're simply ignored, and that's because you're not actually comparing like with noble gases, because the bonding is just weak intermolecular forces, whereas all these other elements on the periodic table have been done by comparing metallic and covalent bonds. Skipping back, just to quickly make sure we've understood atomic radius. So because we know that electrons are constantly moving, they don't actually have a fixed radius. So how would you measure the radius if electrons are moving and they're not in a fixed position? So what we actually do is, as I said before, you take the average distance between the nuclei of two atoms that are in a covalent or metallic bond. Okay, and then we half that distance, and that there is the radius. So hopefully that has made sense. So here's just some pictures to show you. So here's all your covalent ones here. So these are all covalent bonds here that are comparing, and so it's divided between the two, and so that's your non-metals. And we've done that. Okay, so here's a wee summary of the trend again. So it gets smaller across and bigger down, and so we need to talk about why that is. I might in a second actually pause this video and start again because we're already at 12 minutes and we're about to start the trend. So I'll do that now and we'll go on to part B.